This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay. Welcome to the last stop before your weekend. Thanks for coming along. Today is a fun day. Today's a worked example day. So I'll try to get to the worked example as quick as I can. There's a few things I want to give you beforehand. The first one is an apology. Anyone who is registered in the Thursday or the Friday tutorials, there's been emails flying around today, and you would have seen a system announcement from Carol Barry. The uni tried to book rooms that it shouldn't have been allowed to book. As a result, Thursday and Friday's tutes were double booked already, and so the people who turned up to Thursday were like, why are all these people in my room? We found replacement rooms for both of those days to survive, and Carol's been busy with the university trying to make sure that there is a room for those tutorials. To fix the problem, the people who are enrolled in those tutes received emails to say your tutorial's been deleted. And then those emails also then didn't let you, because your tutorial had been deleted, you then couldn't re-enroll in a tutorial. Take a breath, everything will be sorted out. Those things need to happen so that when the new tute rooms are allocated, you're then able to just be automatically enrolled straight back into them. Also remember, that's just the system and we don't take role in the tutorials. So if stuff like that happens, it's okay for the day that things are broken to go to a different tutorial, or for the week that things are broken to go to a different tutorial. Check with your tutors, check with me, check with Carol Barry. Between the three of us we know the answer, and we can help. So I hope that no one was unduly affected. I know it affected quite a few people, but I hope no one was unduly affected. If you ended up missing content that you needed to go through, get in touch with your tutor. If you don't know who your tutor is, you probably should find out your tutor's name and their email address. The names and email addresses are in the subject outline. There are only two possibilities. One is Jacob, one is Antonio. And their emails are, like I said, are in the subject outline on LMS. So if you have a more Australian-sounding person, that's Jacob. If you have a more Italian-sounding person, that's Antonio. Okay, so before I do the worked examples, or worked example, from experience, I have 5 worked examples available out of today's lecture. I spend quite a bit of time waving my hands and talking about the first worked example, and I leave you guys to work through the other ones, and then talk to me or your tutors if you didn't understand the working. I do that because the first time you see a worked thermodynamic problem, I want to make sure you understand why I structure it the way I structure, why we lay out the thinking the way we lay it out. Before we get into it, I have a few slides to put up on screen, and these are partly, these are looking forward in time, because there's a couple of tute questions that use ideas from a few lessons' time. I group the tute questions together in a certain way for a reason, and so what I do is give you some ideas before we've proven them mathematically so that you're sort of authorized to use knowledge from the future. So we'll do quickly do the new concepts. The last five lectures, we have laid the foundation to begin solving problems. So that's what we'll do today. So that's properties, processes, ideal gases, steam tables. The first law, the non-flow energy equations, and closed processes, which is to say processes where there's no mass flow across the system boundary. Several times now, I've talked about the units of the units that we use, the properties that we use to describe the energy of something. last lesson, we introduced constant volume specific heat, and the fact that it has an adjective in front of it, constant volume, suggests there might be another type of specific heat. So today we'll put up on screen the maths of the constant pressure specific heat because it connects to enthalpy, and there is a problem in the tute set that requires you to use enthalpy. So that's what we're doing here. I will also quickly mention, now that we've said that there are processes, I'm going to quickly mention that there's a generic description for ideal gas processes, that all of the processes we've discussed so far, they fit in this generic format. And again, I'm giving you that information early so that you're allowed to use it in your tutorial problems when you're solving them, and so you don't think, I've never heard this idea before. Even though, in theory, you're allowed to read the entire lecture, the entire subject early, many people don't. So, rather than me talking too much about that, let's get them up there. Enthalpy gets a symbol H. Internal energy had the symbol U. Internal energy is our marker for sensible energy. It's the thing that lets us have a mathematical number attached to the idea of how much energy something has. So it's in kilojoules. And there are times when I want to keep track of not just the sensible energy, but also the energy that's represented by the volume that the gas occupies. Remember we said that the molecules vibrating around is temperature, and it bouncing off the walls is pressure. That pressure represents an amount of energy, and if I want to push a certain bit of mass, a certain volume of fluid around, I need to keep track of the energy contained as it crossed the system boundary. It's called boundary work. The marker I use for this extra type of energy is called enthalpy, and what it has is internal energy and a pressure volume term. We will fully define that in about a lecture's time. So I think it's the very next lecture after the work example lecture. I want it up there so that you've seen it. It can pop out. So if I'm pushing mass across the system boundary, if I keep track of the pressure and volume that pushed across, I can keep track of the energy. So there was an amount of mass came into my system. It had some energy because it had pressure and volume. I can keep track of that on the left-hand side of my energy balance. So I can have heat transfer, work, and the work required to push a mass into the system or let some mass come out of the system. If I grab that P delta V term and take it onto the right-hand side, what I get is Q minus work is delta enthalpy, not delta internal energy. So take it's called boundary work, this effort that it takes to squeeze some mass into the system or let some mass out. If I take the boundary work out and around, and I take note of this definition here, then what I get is Q minus W equals delta H, not delta U. So Wednesday was all about Q minus W equals delta U. I'm saying now that if I let mass cross the boundary, I start dealing in delta H's, not delta U's. That's the idea, and we will fully define and derive that after the work example lecture. In that conversation, on Wednesday, we said on an ideal gas, on a vapor, I would look up internal energy on a table. On an ideal gas, I would use CV delta T for changes in internal energy. CV delta T for changes in internal energy. CV delta T, so CV times the change in temperature for an ideal gas would give me, so this is now this equation here. So I could use CV delta T for changes in internal energy. I could use CP delta T for changes in enthalpy. So we let ourselves use this equation because the definition of CV said I can connect internal energy with temperature. There is another thing we define. Again, we'll define this on Tuesday. There's another thing we define, which is the specific heat at constant pressure. That lets me connect enthalpy and temperature. for an ideal gas, I can go nth delta H is Cp delta T. I give you these tools now to make you legal to work with them, even though I've given you no instruction on how to use them. We will really go through this because being able to use Cp delta T and Cv delta T will be part of your tool set. There is a connection between Cp and Cv, and somewhat magically, it is the gas constant. This is one of those moments where maths all connects and you're never quite sure why it connected. So there are times where this happens, where you see, like Green's equation, you see some maths on paper and there's no particular reason why, when you first look at it, why any particular set of terms should be connected. Cp and Cv are connected by the gas constant, and if you've ever seen in this topic, we also have a concept called the adiabatic index, or the specific heat ratio, which is Cp divided by Cv. We use this number a lot, and so I'm telling you it exists, I'm telling you it has a definition, and we will define, derive, justify, and use it throughout the next couple of lectures. This page is here so that your tutorial problem that involves enthalpy is not bizarrely unheard of before when you get to it. And then once we hit the lectures, you'll get the why is it so kind of answers. I will also quickly tell you there are some other, we've looked at symbols for turbines, we've looked at symbols for compressors. There are a few other devices that get used in thermo a lot. One of them is called a throttle, and its job is to let me drop pressure at a constant enthalpy. So now we needed enthalpy to make that statement even make any sense. And so what I have is, for an ideal gas, enthalpy at 2 equals enthalpy at 1, but I have a drop in pressure. It can look like a tube or a valve or some kind of plug. I tell you these things so that if you read a sentence that says a throttle was used to blah, 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 you go, I've heard of a throttle before, and I know that it had constant something or other. Let me go back and look up what the constant something or other was. I see now, it's constant enthalpy or constant temperature. Two other devices that we use in this subject. One is a nozzle, the other is the diffuser. They are the same device pointing different directions. The idealized picture of them is almost a very good picture of what they look like in real life. If you imagine at the end of a hose, a nozzle would take a large slow flow and accelerate it by reducing the area that it's traveling through. Constant mass, volume comes through, squeeze down, accelerate. So the nozzle's job is to speed things up. The diffuser is the opposite of that. Its job is to slow things down by increasing area. I give you the pictures for them and the words for them so that if you read a problem that says blah, 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 a nozzle was used, you go, okay, I've heard that a nozzle exists and I know that I can go back to my notes to find out what happens. We also have a compressor and a turbine. Compressor has work in. I actually have to spin a shaft to run some fans to squeeze everything down again. So if I'm flowing from left to right, I expect to draw my compressor, getting smaller and smaller because I'm compressing things. The opposite of that is the turbine. The turbine lets things get bigger and lets work out. So the compressor has mass flow in and mass flow out and work in. The turbine has mass flow in and mass flow out and work out. So all of these are how you would sketch these components if you're solving a problem, and also if you're reading a problem that has these words in them, they're not alien to you. The very last bit of theory, I deliberately go through these slides quite quickly because I'm not trying to teach you understanding of them in this lesson. I'll say it too many times. My job is simply to let you know that these ideas exist in our subject so that if you read a tube question, you don't freak out. Knowing that, in a couple of lectures' time, we will fully define them. The last set of ideas is what we refer to as polytropic processes. We've had a look at an ideal gas, and we've had a look at a whole bunch of names for processes: isochoric, isobaric, isothermal. We haven't set up any particular maths for it, except there's a couple of things that are obvious. In an isobaric, so constant pressure process, pressure probably stays the same. In an isochoric process, volume stays the same. An isothermal process, temperature stays the same, so I'm not quite sure in terms of pressure and volume really what happens yet, but I do know I've got the ideal gas law to help me. And we said we have an adiabatic process as well, which is no heat transfer. And I don't mathematically know how to represent that yet. So the shortcut is that for an ideal gas, do you remember 2 pages ago we said that the ratio of specific heats, Cp on Cv, had a symbol gamma. Some textbooks they say K. Not sure why, maybe they couldn't afford the Greek font. Plays the same role. Ratio of specific heat, so P, V to the power something, power what? The power of Cp on Cv, or called gamma. It's called the adiabatic constant, and you use it for an adiabatic ideal gas process to say that if I were to analyse this, how does pressure change with volume? I have a rule, I have some maths for it. Pressure, volume to the gamma is a constant. Okay, that's all fine and good. A polytropic process, now there's an almost pointless word. No one even really knows what polytropic means. I'm sure someone does. I'm sure there's a whole field of people who are terribly excited about the true definition of polytropic. We can state that ideal gases, through basically any process, follow a PV to the something rule is constant. So we'll play with a couple of examples of that. If I say the something is just n, I could set that to 0, infinity, 1, gamma, or any number in between. If I state that all ideal gases do that, if I set it to, let's set it to 0 first, because that's nice and easy. If I set it PV to the 0, then I just have P as a constant. So V to the 0 disappears from my equation, turns into 1. Then I have P as a constant. That's an isobaric process. If I set it to 1, PV equals MRT. If I take away the M, P little v equals RT. If I set it to 1, then what I have is an isothermal process. If our temperature was constant, PV equals a constant. So if I set N to 1, I've got an isothermal process. If I set it to gamma, I've just defined that if I set it to gamma, I've got the adiabatic process. And if I set it to infinity, there's a weird one. Mathematically, this is a weird one. If I set it to infinity, the volume term is so important that the P1 can be ignored. What I have is V is a constant. Infinity is a weird number to play with, so you partly just have to accept my word for this. But the message is, for an ideal gas, all the processes it can do can be mapped up by PV to the something. We have this rule, we have this statement because it allows us to generalize a whole lot of our maths. When we derive things, we can say, is this true for all processes? Yes, it's true for all processes if I say PV to the n is all processes. And then I can do all sorts of integrals and what have you. Again, that idea is up there, so that if you read a tube question that's got the word polytropic process in it, or adiabatic process, I think there's one tube problem that has adiabatic process and requires you to do some integration. You need something to put in there. Now you've got the rule. It's almost cheating on my part. In one sense, it's also jumping around too much. But I'm happy with the way the two questions are lined up, so I want to give you all the tools, at least the information to solve them, before we bog ourselves down in the mathematical definition. All right. I'm going to tap through the five example questions on the screen, so you see what exists in this lecture and what exists therefore in the worked examples that are on the notes. And then we'll do one of them nice and slowly, and then if we've got any time, we'll do another. The first one is a steam example, and you get a thermodynamic question. It's full of code words that we will unpick one by one. Two tanks that are separated by something, and then you take the separation out and let them all mix, and try to tell me things like what's the final temperature, how much vapor is there at the end, how much heat transfer was there. You'd be surprised to know that right now you have all the tools to solve that problem, and so we'll come back and do that. An ideal gas problem, saying nitrogen at a certain condition is compressed with a process code word, isothermally, in a piston cylinder, determine how much work that took. And the answer's up there, and you have all the tools right now to do that. There's a question that says we're boiling water, and I lose some water during the boiling process. Work out what rate I was adding heat to that pan. So it's taken me 45 minutes to boil off 10 centimetres of water from here to there on a 25 centimetre diameter pan, all sorts of information. Immediately your brain starts saying I could do volumes, and therefore I could work out the volume lost, and I have the time it took, so I have some connection to a rate instead of an energy total content. Also I have the tools to work out how much energy that took, and therefore the rate, which is the power. This one we need the idea of enthalpy for. And then there's also two worked examples, one on a nozzle and one on a turbine. Same shaped device, except one has work coming out of it, and the other is just a thing to accelerate a flow. So the nozzle, I've got stuff coming into a nozzle. Remember, nozzle takes slow stuff and makes it faster. Stuff coming into a nozzle with a low velocity, code word meaning velocity is approximately 0. It's steam with a certain quality. We tried to define quality at the end of one lecture ago, which is the percentage amount boiled, percentage mass boiled. Find the exit velocity. There's not a lot of information there. In fact, I don't even know the area ratio. But you have all the tools to be able to solve a problem like that. There are tricks in that problem that people almost always get wrong, which is why I give you the answer, so you know when you're getting it right or wrong. And you've got the full work solutions, which I think I've scribbled an arrow saying, don't get this wrong. Turbine problem says, I've got a turbine, I've got high pressure air coming in and low pressure air going out. I give you the code word, it's an adiabatic process, and I want you to calculate the work done per unit mass, and I give you 3 different ways to evaluate it, which is to say 3 different approximations for the process, and so you need to talk about how different they are. So 1, we use temperature dependent data, 2, we use CP average, 3, we use CP at a certain temperature. This is all brand new ideas. And so it's completely okay if you look at that one and go, I don't even know where to start. And then you look at the worked example and you say, I still don't know what happened. They're there so that when we cover the enthalpy problems and start playing with these different terms, you have a worked example to play with. I put them all into this package of notes, so if you want to read ahead, sometimes it happens, you've got examples that you can play with and see the fully worked solution now. If there's ones in here, as you go along, that you want to see scribbled down in front of us during a particular lecture, if you get into them, start emailing me, start telling me, could you please do blah, blah, blah example. If we don't get, I know we won't get through them all today, but if there's ones that particularly jump up, let me know. It's also okay to take the printed worked example to your tutor or book some time with your tutor and say, can you walk through this with me? So let's go back and do the steam one first. So I'll leave that up on screen. I will reproduce this information on my scribbled answer, on my document capture answer. But for the moment, let's read through it and let's just pick out a couple of code words. So the major code words, I got 2 tanks that are separated by a partition. You don't need to know what a partition looks like, just that it is some kind of barrier or separation. It could be a piece of plastic, it could be a piece of metal, it could be a disc that I lift out of the way. We begin just with the idea that you've got two tanks that are separated but close to each other. I give you how much mass is in tank number 1, at what pressure, at what temperature. I give you tank B, how much mass, saturated liquid vapor, mixture, so it's got water and gas, at 150 degrees, and I tell you what ratio of water to gas it's got. I tell you that it's got a vapor mass fraction, which is another word for the quality, which is another word for the percentage amount boiled, of 50%. Now I take the partition away, or pop it, or remove it, or something. The two tanks are allowed to mix until mechanical and thermal equilibrium, pressure and temperature, are established. If I tell you the pressure of the final state, tell me everything else. So there's a lot of code words going on there. And at the moment, we haven't spoken at all about how you structure your writing, how you structure your answers. The most common thing for an engineer let loose with a problem like this is to start randomly doing little calculations around their page until some picture starts to form. And then you go, what was the problem again? What was I trying to solve for? Wait, I don't have that. No, I'm missing a piece of information. And you scribble some more stuff. And you go, wait, was I supposed to use property tables? And you look up the property tables. Yes, I was. And then you find something else and you scribble a note. And then you label one A and you label another one B. And you say this one's 1B and 1A. And eventually you write a little note at the bottom saying answer, scribbled underlined, saying 1A plus B plus C divided by 2. And you might have circles and lines drawn over. Because you didn't structure your working, and you look at it, and you go, yeah, I got it, because my answer matches. And you get 6 out of 10. You go, I don't understand why I got 6 out of 10. You don't realise you made a mistake here. You didn't state assumptions there. You didn't lay it out nicely. Some of your stuff was unintelligible, and you made a mistake somewhere that no one could follow. So I'd like to begin with some base assumptions around how to structure your work. I understand this is not the only way to solve a problem. It's just this is what I'm about to show you is the first half page of almost every problem that lets you keep track of all the stuff. It lets you keep track of all the ideas. Where did I put my pen? There it is. So let's get this guy up on page. It's gone dark again. Good. Okay, that's here. I'll zoom out. I've got a big long page. I'm just showing you because I'm going to occupy about this much of the page with not answering the question. And I'm going to earn myself points on the way. And I'm going to make sure that I don't lose track of anything on the way because I've laid out all my stuff nicely. So let's transfer all of the information we were given in the question onto the paper in a way that helps me. The structure for this is a couple of things. I want 1, a diagram, 2, data, 3, laws governing equations, 4, assumptions, this one's hard, and 5, goals. This is a structure for laying out the beginning of a problem that has nothing to do with answering the problem. If I put this information onto my page, I have a well-structured question that has not even begun to calculate anything. And yet I've already started to get marks for the question. There will almost always be marks for having a useful diagram. Often the diagram will be on a property diagram like a PV or TS. Sometimes it's just a sketch of the system. For an engineer, a sketch of the system is really valuable because it lets me see really quickly whether you get what we're talking about. it lets your boss see really quickly whether you get what they were talking about. You've had a conversation and he says, please analyse this, and you draw a sketch and he says, where's the inlet? You go, oh, I didn't realise you're talking about an inlet. Boom, you've communicated. You've solved a problem before you waste 3 weeks trying to solve it. So we had 2 tanks. So I'll draw 2 tanks. I don't need to draw pretty tanks. I need to draw 2 boxes separated by a partition. And I'll call them something. Tank A and tank B. And I'll call them tank A and tank B because the question called them tank A and tank B. I was told that something happens. So I'm going to do tank A and tank B at state 1. And then they say something happens. I remove a partition. And I have a condition at state 2. So I'm going to draw another box. These are not process diagrams. These are not property diagrams. This is tank A plus B, state 2. So I'm drawing a diagram. Now draw some data. I could list the data, or I could sketch it onto that diagram. I like to sketch things onto the diagram. I was told this guy had a mass A of 2 kilograms. It had a pressure A1 of 1 megapascal. It had a temperature A1 of 300 degrees C. I'm not suddenly trying to turn any of this data into another unit. I read 1 megapascal, I'll write 1 megapascal. I read 300 degrees Celsius, I'm not trying to turn it into Kelvin right now. I'm just transferring the info from here to here. This guy had mass B equals 3 kilograms. This guy had temperature B1 equals 150 degrees C. And X, it said the vapor mass fraction was 50%. Our unit for quality, or vapor mass fraction, is X. Our symbol, sorry, equals 0.5. When I've got A and B, I'm told pressure 2 equals 300 kilopascals. Now I've drawn a diagram, or 2 diagrams, and I've got some data on the page. My next thing, some laws or governing equations or assumptions. I'm not an absolute purist about this. I'm not going to freak out if you write down some things and then realize you want to write some assumptions, then write some more laws, then write something else. Or if later you realize you should have written an assumption, you have to go back and write an assumption. But leave some space. Leave some space for this stuff before you start answering the question, so that if you need to pretend that you always knew the assumptions, you could go back and make it look like you always knew. But up here, we're going to say we're going to be using the properties of steam, because I was told this is a problem with steam. In the question it said steam in a tank. It didn't say nitrogen in a tank or air in a tank. It said steam in a tank. And so we're going to use the tables to answer the question, which is therefore not an ideal gas. I'm going to assume fixed height and fixed relative velocity. The first time you solve these problems, you won't know to write that assumption down. Probably the second time and third time, you won't know to write that assumption down. I need that because when I start to deal with energy, if you remember when I did the energy conservation laws, I said we have heat transfer and work equals changes in energy, and I define that as internal energy, kinetic energy, and potential energy. Most of the time, I want to be able to quickly say I'm not thinking about potential and kinetic energy. So at some point, most of the time, I'll have a little assumption that says, the quickest way you can write this is delta KE approximately equals delta PE approximately equals 0. There's a whole bunch of shorthand you can use to say I'm neglecting kinetic and potential energy changes. I will use a few things. Now, again, you could try starting to solve the problem without stating exactly what laws you'll use. I write these down now because I've been doing this for 20 years. The first time you write them down, you might not know to write them down. So this is the beginning of forming good habits, even though I'm not expecting you to know this instinctively. If you knew it instinctively, you wouldn't be in class. Using conservation of mass and energy, or first law. I'm also going to say this is a fixed volume closed system. Stuff's starting to disappear off the top. That's okay. Find, I'm now up to my last point, the goals. Find a T2 and X2 if saturated. Find then Q out from 1 to 2. Let's zoom out a little bit. There's the bottom of my page there. My thumb is about halfway down the page. I've started writing. It's my exam. I've filled up half a page of my exam page on this problem, and I have not started to solve the problem. And yet I've already got, in the rubric, I will have already got at least 2 out of the 10 marks from having nicely stated some stuff and also put down some diagrams that make it clear that I know what I'm doing. Are they the right diagrams? Does such a thing exist? The wrong diagrams exist. There are times where you put down a process on a diagram and it's quite obviously wrong. If it was supposed to be constant pressure and you didn't draw a horizontal line, it shows that you didn't get the question. If I draw prettier tanks or uglier tanks, that's okay, provided I drew tanks that make sense. The other thing that's happened here, if I wrote down here, mass A equals 1 kilogram, the question said mass A equals 2 kilograms. From this point on, I've only lost half a mark for having written down the data wrong. And it's really easy for me to see the error and where it's going to propagate, and that the rest of your working follows the logic fine, is using the maths fine, is using the right tools fine. So in my assessment of your thermodynamic skills, all that I see wrong is that you can't read or can't write, but I can see you can think and you can choose the right tools to solve the problem. That's different to having no idea where things went wrong, which is to say just seeing the answer and going, now I have to backward calculate all possible scenarios that could have led to that answer to determine where you got it wrong, and then try to work out whether it was a little thing or a big thing, an understanding or a transcription error. So we waste the time like this to make everything clear. For an assignment and for an exam situation, there's lots of different pressures on you. There's time pressure. There's reasons why you might not do this. If you get the answer right, it didn't make much difference whether you did this or not. If you get the answer wrong, it might make a big difference as to the amount of marks you got. This is not the only recipe for laying out and structuring your question. But if you leave, remember, you could submit, imagine you were submitting an assignment that had 10 questions and you submitted 20 pages because you were so spaced out with your writing. That's okay. If you submitted 10 questions on one piece of paper that just had the answers, that's not okay, because the moment you make an error, I have no idea where you made the error. Take your time, make space. If you wanted to leave space for assumptions and you don't remember all the assumptions or you're not even sure what they were, leave some space so you can go back and write them down. We have not started to solve the question. And we are well into writing down a whole bunch of stuff about solving the question. Now, solution. My goal is to find temperature at 2. Let's think about it. I put my pen down and I talk to you a bit. With everything we've learned about properties and everything we've learned about state, what do I need to determine the properties of a system? intensive independent properties. So I'm hunting temperature, so probably temperature I won't have. Right? If temperature is the thing I'm looking for, I won't have temperature. I either need to calculate it or know enough about the system that I could look up temperature. An easy way to find temperature is if it's boiling and I know the pressure, I know my temperature. If it's not boiling, if it's somewhere superheated, I need to know something else. I need to know I've got pressure, so that's one. I just need one other thing. One other independent thing will let me pin down the state of 2 and therefore work out any other property I want. So, our job on this question, the job to answer part A, is the hunting of something else, of the something else. I've got pressure, and I just want one other piece of information for me able to find temperature. I've got all these wonderful tables that I could look up the 300 kilopascal table. I could look up 300 kilopascal on the saturated pressure table for steam. I could look up 300 kilopascals on the superheated for steam. I don't know whether I'm superheated or not yet. So I need to know something else about the system, and hopefully, hint, yes, hopefully there's enough info about the initial conditions and the process that I can work out what the final was. But I don't know which property I'm looking for yet. I don't know whether I'm looking for entropy, enthalpy, internal energy, specific volume, density, same thing. I don't yet know what I'm looking for. So I start to play some games. My first thing I'm going to write down, I said I was going to use conservation of mass and conservation of energy to try to solve this. So I might as well write them down. The mass one, conservation of mass, is almost easy, almost always trivial to write down. Sometimes so trivial you forget to write it down. You sort of assume that everybody knows. So you say that. So let's go. Conservation of mass gives me that M1 equals M2, which is to say that MA plus MB equals M2. Okay. I'm not there yet. I don't have an independent property, but I've got something, and I might use it later on. When I look at my working. Sorry? Yeah. Yeah. How's that? Actually, I can zoom in mode. That's crazy. Let's go crazy. Cool. Conservation of mass. Mass at the beginning has to equal the mass at the end. Nothing tricky to it, but I haven't finished. I haven't solved my problem. And we're in thermo, so I probably need to do something about energy, so let's do conservation of energy. So first law, I'm going to move this all the way up. I could jump straight into writing the non-flow energy equations. I could write N, F, E equals Q minus W equals delta U. Because I've authorized you to do that. In the development we did to say if you prove to me it was a closed fixed boundary problem, you can jump straight into writing the NFE. I like not doing that because I like not losing track of my assumptions. So I like starting at En equals E out equals delta E. Energy in minus energy out equals delta E. Then I like writing all the stuff, particularly the first time that I show you something. Q in minus Q out minus, well, let's put all the energies on this side. Work in minus work out equals U2 minus U1 plus delta KE plus delta PE. And let's start crossing things off. Heat transfer in, don't think so. Heat transfer out, I'm looking for 0. Any work done on the system? No. I did not put a paddle in there. I did not put an electrical current in there. I did not do anything here, so no work in, no work out. So what I'm left with is, remember our convention before, which was that work out and heat in were positive? So if heat out, I'm going to leave my minus there to remind me that if I work out heat out, if I determine a value for heat out, I'll flip the sign, equals U2 minus U1. Okay, this is my tool for solving the problem. Note, I haven't written it down in specific energy terms. I've written it as total energy terms. So what I need to do to solve this is to understand U2 and U1. This guy here, in my conservation of energy equation, I've got the answer to part 2. So what it looks like, again, I'll pause. What it looks like is, on my journey to solving part B, I will probably find the answer to part A, which is to say part A is bonus points for getting to the end, and a guide as to which bits might take more work. If it's going to give me actual marks for the question for determining something that's just on the way to the answer, it's probably going to be tricky. There probably needs to be some extra effort. So, this means we need to find U2 and U1. If I have U2 and U1, I have the heat transfer. So what do we got? Do I have, let's take a look at state 1. Tank A, tank B. Let's look at tank A. This, I'm trying to solve for the answers to state 2. So let's take a look at state 1 and tell me whether or not I have, for tank A, 2 independent intensive variables. So you're always giving me the right answers, which is why you answer, and then I look around the room to see whether people are nodding. I want more than just one voice saying yes. So what are they? Not you. Sorry?
Pressure and temperature.
I got pressure and temperature. Now, is there any indication, is there anything about, are there any times when pressure and temperature are not independent? Yes. So how do I know that these ones are independent? There's nothing in particular in the question that tells me that it is, but I have all the tables. Now, I'll save you the time looking up the tables. If you grabbed the megapascal table from the superheat or the megapascal line from the saturated and looked at the temperature, you would straight away see this is superheated steam. Which is to say, if you grabbed the megapascal line on the saturated steam table, it would tell you the saturated temperature, and you would see that 300 degrees Celsius is far above the saturated temperature, which tells me I'm superheated steam, and that tells me that tank A is fully defined. I got temperature and pressure, and I'm good to go. So there's nothing in the question that confirms absolutely that we're good. You have to do one, just confirm, you have to confirm for yourself. Tank B, it tells us it tells us a quality factor, a vapor mass fraction. So basically it tells us that it is boiling, in the process of boiling. So it gives me the temperature and one other independent variable, the quality, and that's enough to pin down the state. So tank A and tank B, I have 2 independent intensive variables, which means tank A and tank B are fully defined, which means I can determine their internal energy from the tables. I look it up. One of them I'm looking up from the saturated table, one of them I'm looking up from the superheat table, which means I have U1. Once I get those numbers and I multiply them by mass, I have U1 for state 1. I have the internal energy of state 1, and then I'll need to work out the internal energy at state 2. So we'll get to that tricky point first. So, 1, let's get little u, A1, is, I write my table notes over here. So I write P equals 1 megapascal, T equals 300 degrees C. If you were to go look them up off the table, you'd find superheat, and therefore U1 equals 2793.1 kilojoules per kilogram. And I need some space. That's a number. You can write it down if you want. It's also in your notes. Conscious of time, I will move as quick as I can. Okay, so this bit maybe don't try to copy down as fast. So UB1, little UB1. So this is a specific internal energy of tank B at the beginning is UB fluid plus XB1 UBFG. This guy is on the table. This guy is on the table. This guy was given to us, which means I can calculate this guy. So that was 631.66 plus 0.5 times 9. There's a lot of numbers in thermo once you actually start solving problems. And so there's a lot of places you can make mistakes. 1594 point, for example, 5.4 kilojoules per kilogram. And so big U, 1, is equal to the mass A times UA1 plus mass B times UB1. Plug all those numbers in. I'm going to save myself a line by assuming that you could do 2 times the number and 3 times the number, and I get 10372 kilojoules. I'm not finished yet. Sorry, that wasn't a pointed comment. You're welcome to leave. I'm not finished yet. I've just got the internal energy of state 1. I still need the internal energy of state 2, and now we need a trick. And so our trick is to get U2. We're given pressure, we need something else. What do I know about state 2? What would be a good number? If I had internal energy, I wouldn't need to solve anything, so I probably don't have internal energy. Enthalpy and entropy I haven't learned about yet. So now I've got a bit of a shortcut. What's left? If I had specific volume, we'd be sweet. But I don't have specific volume. This bit's easy. If you've got the work notes in front of us, you already know what the answer is, right? I'd like to have V2. So where do I find it? What is specific volume? Volume per unit mass. And so if I had V2 is the volume of 2 over the mass of 2. Do I have those? Do I have enough info to work them out? Do I have the mass? Yes. Good. Excellent. We're off to a roaring start. I've got the mass. How do I get the volume of the tanks? I took a piece of paper out from between the two tanks. So I didn't change the total volume of the original system. So if I were able to work out the volume of the tank A and the volume of tank B and add them up, I've got the volume of tank AB. How do I get the volume of tank A? I've got the mass that was in tank A. If I had the specific volume and the mass, I could get the volume. Tank B, if I had the specific volume and the mass, I could get the volume. So I have enough now to be able to then go ahead. So vol of the tank is vol. I could just write V, but it's easier for me to write vol VA plus vol B A. And if I do a little bit of maths, vol A is specific volume times mass, and I get 2. And I would look up the specific volume off my table because it's listed 25799 times 2. Vol B is trickier because I need to interpolate at 50% of the way between two specific volumes. But the same process, mass B, I'm now racing a little bit to hit that last minute, mass B times times VBF plus XVBFG, etc. And I end up with 3 times 0.001091 plus 0.5 times some more numbers. All the numbers are in the work solution, so bear with me. Then I get 0.59 here, and here I got 0.5160. 5160. Put it all together, I get volume 2. I've got mass 2, I get specific volume 2. Specific volume 2, 0.2216. Then I look it up. and I find out that this guy is in the saturated region. So I've got my 300 kilopascals. I pick up my saturated table for pressure, for steam. I see there's a 300 line.